Federico Larroca is an assistant professor at the engineering school of the Universidad de la República, Uruguay. He was a research engineering postdoc at Telecom Paris Tech during the first quarter of 2010, where he obtained his PhD in computer science and networking under Professor Jean-Louis Rougier in December 2009. He received the degree in telecommunication engineering in 2006 from the Universidad de la República, with a thesis concerning the development of a propagation model and loss prediction software for cellular signals in suburban and urban environments. From 2004 to 2011, he held a teaching assistant position at the Universidad de la República. His current research interests are related to the analysis and modeling of communication systems and development of software-defined radio.
Hello everyone, welcome to my talk. It's called Ultra-Cheap SDR Digital Television Transmission, ISDB-T, with an osmo-fl2k and an RTL-SDR. So this is a joint work with Pablo Flores, David Artenstein, Lucas Inglés, and Gastón Morales. We are from the Instituto de Ingeniería Eléctrica, the Electrical Engineering School Institute at the Engineering School at the Universidad de la República, that's the Republic's University of Uruguay. So, to start with the talk, we all know that there are plenty of TV standards. There's ATSC at the US, there's DVB-T in several countries, Europe, Africa, Asia, Oceania, even South America. And there's also, DTMB and ISDB-T, that's the subject of our project. That's mostly used in South America and a couple of African countries and some Asian countries, including Japan. And so just to give like some motivation on our work, there are many benefits on digital TV transition, that is on turning off analog TV transmissions, particularly the increased spectral efficiency. Here I show the ongoing transmissions here in Uruguay of both analog and digital channels, and we can see how on the right we can see how the digital TV channels use much more efficiently the spectrum than analog ones. So what are the benefits of digital TV transition is well, it brings on much better audio and video quality on the same spectrum, and regarding money, to say it in a way, it brings the so-called digital dividend. That's like the auction or the reuse of the spectrum currently used by analog transmissions. So although we just mentioned several benefits of digital TV transition, this transition is long from far from completed. So this is a map showing the transition stage, to say it in a way, and you can see in yellow it's where it's in progress, where both analog and digital transmission are going on, and you can see how in the countries that ISDB-T is being used, except in Japan, the transition is still in progress. Particularly in Uruguay, actually the situation is that it's indefinitely paused. So we have no date to turn off analog transmissions. So we're currently transmitting both types of TV. So in this context, back in 2016, we presented GRSDB-T at WinCom, the WinCom conference, and it was back then an open and free receiver, only the receiver side for ISDB-T, implemented naturally on new radio. So we are now presenting the say completion of the project. It's an SDR-based open source ISDB-T transmitter. So what for? Well, you can probably think of many uses for a complete transceiver now. So it's transmission and receiver and reception. But let me just say three main reasons that drive our project. First, in order to gain a real understanding of a certain technology, I believe, especially since I work at a university, that no real learning or no real expertise can be achieved without actually using the technology. However, we here in Uruguay, we don't manufacture or design or receivers or transmitters. So let's say the only alternative is this, to use an SDR-based system. Furthermore, in particular for ISDB-T, a complete transceiver has many uses, specific uses. For instance, transmitters, chip transmitters, which for community channels maybe we've been asked for by many community channels for how to transmit using ISDB-T. It may also be used for simulation to choose some of the parameters involved in the standard, how to choose them. Well, we may first simulate the complete system, a very detailed simulation in this case, and then deploy or configure the system to use these parameters. And the last item, and related to the introduction, we hope that the availability of both the receiver and the transmitter that's open and certainly inexpensive should accelerate this digital TV transition. So let me present very rapidly the ISDB-T standard. So it stands for Integrated Services Digital Broadcasting Terrestrial. It was originally designed in Japan. It's relatively based or heavily based on DVB-T. And it was later adopted and adapted by Brazil, which, for instance, the two most important differences from the original standard was the introduction of Shinga instead of BML for interactivity and a different source coding. And this new version was called ISDB-B or ISDB-T International, and this is the version that most South America countries and around the world actually use. But regarding our project, there's no real difference between ISDB-T and ISDB-T-B. So this is the system flow graph. Let me just, and there are several parameters in the table on the right. Let me just go through this somewhat step by step. So a first important aspect of ISDB-T is that it transmits three different transport streams simultaneously. These are called layers, and each layer has like its own transmission path, where, for instance, the convolutional coding rate or time interleaving depth may be chosen differently for each of these transport streams. And given this characteristic, the ISDB-T defines what's called a broadcast transport stream, which is a variant of MPEG transport stream, since the original MPEG transport stream cannot be used for hierarchical transmissions. So this is like one of the most important characteristics of ISDB-T. Then we have somewhat standard or OFDM system. The sampling rate is fixed. Now there is a which is related to what I mentioned before. Each of these layers is sent over a set of particular carriers, and these carriers are partitioned into segments. In particular, there are 13 possible segments, and each of the layers is sent over a subset of these segments. And finally, well, the sampling rate I mentioned is fixed. There is a configurable cyclic prefix, and the resulting bit rate per layer is per segment, sorry, is in the table. It's between 300 kilobit per second to say a little bit less than 2 megabits per second. That's per segment. So depending on the configuration, but it's a maximum of that number times 13. So there is a second very particular thing on ISDB-T, which is the one we're going to show later, that the designers of ISDB-T were very interested in handheld receivers. So I'm showing here some real ISDB-T receivers. For instance, to the right there is a PlayStation Portable that includes like a I don't know, accessory which enable the PlayStation Portable to receive terrestrial television. And how this works is that this is the so-called one seg feature, and if this feature is enabled, what this does is that the central segment, only just the central segment, it's marked here with segment 0. Just that segment may be received on its own. Why? Because it is frequency and time interleaved independently of the rest. Moreover, the complete signal, even if low-pass filter, is still an off-DM signal, so the receiver is mostly identical, except that it works at a lower sampling rate. And all the pilots and signaling are present on all segments. So regarding that aspect, it's really not necessary to receive the whole 6 megahertz signal in order to decode just the one seg portion. So that's it for ISDB-T. Let me just talk a little bit about our implementation. This is like the complete flow graph. It's somewhat messy, so I'm going to go through some of these blocks. Let me start by the say to the left. It's the video signal, so in a way. So that part takes the BTS, that I mentioned before, and outputs, in this case, the 3 MPEG transport streams. So if one wants to transmit a single video, so that's like a single transport stream, it's not really necessary to use this part of the flow graph, and one may simply input that single transport stream to the rest of the flow graph. So I'm going to talk about that on the conclusions too, because that's like one of the parts that's complicated, as to say it in a way. Then there are some relatively standard blocks. They mostly correspond to the ones I showed before. There's the encoder, the byte interleaving, current modulation, and let me say that there are some blocks that are already part of new radio, and we've reused them. Especially there are some that are part of the GRDTV module. Then we include, as I mentioned before, pilots and signaling, OFDM modulation, and normalization and transmission. So that's like the flow graph. It's once you have the idea of which blocks do what, it's relatively simple. We tried to make it correspond each of the blocks to one of the blocks on the standard, so it should be relatively easy to read the flow graph. So now let me talk about the presentation's title. So we've tested the implementation with SDR transmitting capable hardware. Particularly, we've used USRP-V200s. We've tested with other hardware, but we were. Let me just show a little example. Since as receiver we've used both TVs, commercial TVs, as well as others SDRs, including RTL-SDR dongles, which we've set up the flow graph to receive only the 1 sec portion. So let me show you this little video. This is David.
Probando.
Using the pre-encoding the webcam. You can see how you can see the delay it's generated. That's due to the re-encoding of the webcam plus the whole flow graph transmission. So it has like a relatively large delay, some seconds. But we were particular that was made transmitting with a USRP-V200, but we were particularly interested in using the osmo-fl2k project. So what's the osmo-fl2k? It's they're using a very cheap USB to BGA adapter as an SDR transmitter. How does it work? Well, the idea is basically the same as with Tempest. In case you don't know Tempest, let me just show you a little demo of our own GR Tempest. The idea is there is the telescopic antenna, and it's receiving the signal emitted by the BGA cable that's maybe seen over there. We are using here another USRP, a mini, and the objective of Tempest is to spy on, to receive the images on the monitor through the electromagnetic emanations from the BGA cable. So you can see there how the image is relatively clear. You can see the letters that's being typed. But in this case, in the case of osmo-fl2k, the idea is that the BGA cable the BGA is now emitting on purpose. So the project is based around the FrescoLogic FL2K chip-based adapters, which has the particularity that all samples, including blanking, are generated by the host PC. So this is like a sort of software-defined, I don't know, the analog to digital converter or something like that. So what they did is they reverse engineered the USB protocol, disabled blanking, and provide the necessary software to send arbitrary samples to the USB adapter. So, as I said before, it's like now we have like a software-defined digital to analog converter. And if you take a look at the spectrum of the generated signal, it looks something like this. So we have in black the Fourier transform of the pulse, because say the converter, if it's a rectangular digital to analog converter, the Fourier transform is going to be like a sink, no? Then we have in blue the discrete time Fourier transform of the pixels sequence, which is what we're going to inject or transmit, or we are going to try to transmit. And what we actually get is the multiplication of both the blue and the black functions. So that's the emitted spectrum, that's in red. And the problem we have, and the problem that we saw when I showed the video of the GR Tempest demo, you may have noticed that the image was like very distorted, and that those distortions are generated by this frequency null right here due to the form of the pulse, which maybe it's not perfectly rectangular, but it's going to be somewhat rectangular, so those nulls are going to be near, or it should be approximately a null at the pixel frequency. So how can we solve that problem? This problem of those nulls? We simply use like an intermediate frequency. That's what I'm showing to the right. It's a very simple flow graph where we take the signal and simply instead of say generating baseband signals, we simply change it a little bit or offset it a little bit in frequency so that to avoid these nulls. And another thing I want to highlight is that note that there are harmonics every pixel frequency. So that's if you're going to transmit and you probably don't have the license to transmit at every harmonic pixel harmonic frequency. So beware of the harmonics. That's one message. So let me just show you like a little demo here. It's only a couple of minutes long. So this is the flow graph that I've shown before, where we are generating this sort of intermediate frequency signal from the ISDB-T original flow graph I showed before. So now we are using the software provided by the osmo-fl2k project, where we are sending those generated samples to the adapter we're showing here. Then we've connected just to work comfortably BNC adapter, BCA to BNC adapter, which is connected to an amplifier. I'm going to talk about this, or why this is necessary in just in a moment. A very simple antenna. We were interested in say testing it, very simple setup with very cheap and simple antenna, and you can see we are receiving this HD signal on the TV, and we're going to this should move in some seconds. There it goes. We are also receiving the 1 sec part of this 6 MHz signal on an RTL-SDR dongle, and this is going to run the 1 sec reception receiver flow graph we are sharing on our repository GitHub. And as you can see, we're also receiving the SD signal that's being transmitted on the single segment on the right in the middle that I've shown before. So this demo, we are transmitting 2 layers, an HD layer using 12 segments, and the 1 seg signal using just the central segment. So the end of the video is just to show that both signals are received at the same time by both the TV and the near radio flow graph. So to conclude, to sum up, well, I've just presented GRSDB-T, which is a software-based free and open ISDB-T transceiver. We are very happy to have successfully tested it using the osmo-fl2k as transmitter. However, there are some important things to take into account if one wants to say experiment with this project. So first, the transmitted signal is distorted by the pulse. I discussed it before, how to avoid the nulls, but the sync is not a constant. So it's going to be somewhat distorted. FDM signals are easy to equalize, but single carrier schemes, for instance, are going to be more challenging to use with this transmitter. So some form of equalization should probably be used. Then the second thing I wanted to highlight is that since there is this sync form, only the first and maybe the second, but probably mostly the first harmonic has enough power to be usable for wideband signals. So if I didn't show that demo, but we've also implemented a just one seg transmission, so that the whole power of the whole, what little power it can transmit, it's focused or concentrated on one segment. In the demo I've shown, the whole power is used on the whole 6 MHz signals. So in those cases with wideband signals, only the first harmonic is usable. Up to VHF band is like the highest frequency. In our experience, you can work with the osmo-fl2k. For instance, the demo I've shown before, it was using 177 megahertz, and it was, you saw the constellation. It was relatively noisy, and even using the amplifier. So the amplifier there was used because we needed to transmit at this relatively high for the osmo-fl2k frequency, so that the TV may receive the signal and decode it. Again, I'm going to repeat it again. Beware of the harmonics. Probably a filter. You will probably have to use a filter if you want to transmit using this osmo-fl2k. So the third caveat is that the signal has to be upsampled to the pixel rate, which is about 150 megasamples per second. This is to match the signal sample rate to the DAC, no? So with these very high sampling rates, live transmissions, say use the whole ISDB-T transmit, the encoding, the whole flow graph, plus this upsampling, it's going to be probably too much for any computer. So except simple waveforms such as FM and FM radio, it's a live transmission. It's going to be virtually impossible. So what we did is we've recorded this upsampled signal, and then we've used the software which is provided by osmo-fl2k. So for future work. So the first thing is that, as I mentioned before, ISDB-T use BTS, which is like a very special type of transport stream. As far as we know, there is no open source software to generate BTSs. So if no BTS encoder is available, we were helped by one of the TV enterprises that works here in Montevideo, which generously lend us a BTS to test, in fact several BTS to test. If that's not a possibility to have an encoder, you may either use a single carrier transmission, single layer transmission, there's a typo there, but single layer transmission, because there's no need for a BTS. Or you may send several transport streams without encoding BTS. Now, there you'll have certain TVs will receive the signal correctly. Other TVs won't. So that's what I'm saying there, that this is TV set dependent reception, because what we think it happens is that certain TV sets will try to remake the whole BTS and then decode, and other TVs will simply take the one of the transport streams and start decoding. So the simplest thing, if you want to test the transmitter, is to use a single layer transmission. So the other future work is first the current implementation is for New Radio 3.7. So I should start migrating it to New Radio 3.8, and I will as soon as I have time. But I think that it's finally time that we integrate the whole project to GRDTV. Thank you very much for your time. I'm not sure how the questions will work in the virtual conference, but you may send me an email. There's an email here. You may contact me through Twitter, and that's my GitHub account, and there's our repository is also with GRDTV. ISDB-T is also there. So go ahead, download it, and test it, and give us feedback. We're always interested in feedback. So thank you very much.